Good evening, class. Uh, this will be the second last class, as you know, for this coursework. And in today's class, I'll be discussing about the superconductors. So the last class was also about superconductor. There we discussed about the Meissner effect and the types of superconductor, type 1 and type 2. Today we'll be doing some numerical calculation based on it, and of course we will discuss the Meissner effect maybe in detail slightly. And along with that, there will be some question based on the penetration length. And so, having said that, let's first go through the previous class questions which I phrased. So, what are the two materials which are type 1 and what are the two materials which are type 2? Anyone who would like to answer these ones, because they are the question which I asked in the second class to read about those things. Is there anyone who would like to answer this? They are easy search on internet also, but I just wanted you guys to know these type of superconductor at least to search by yourself. Is there anyone? I don't see anything coming out in the chat box list. Okay, so the second question was, where do these lie? Aluminium and mercury. So, of course, if you just search it on the internet, you will find the answer that aluminium and mercury, they are type 1 superconductors. Aluminium, mercury, lead, all these are type 1 superconductors. Where the one which are like niobium based, they are mostly type 2 superconductor. Like for example, if I write the type 2, it will be niobium titanium, of which generally these superconducting magnets are made. So whatever you see in your MRI machine, dilution fridge where you do these experiments, so they are like niobium titanium. The reason being they are used is they have slightly higher uh, critical temperature, so below which they are superconductor. So that's the reason. And niobium based, like niobium zirconium based, all those, I think NBSC2 also falls in this one. So niobium based, these are the type 2 superconductors. So in the type 2 superconductors, there will be vortices. They can allow a certain field to pass through it, through the vortices. Whereas in the type 1 superconductors, there will be perfect diamagnetism, and after a certain threshold magnetic field, the field will penetrate and there will be complete expulsion. There will be like complete destruction of this superconductivity. That's what they're in the type of superconductors. And I would say that you guys should read on these questions at least, because they will be important for your exams also. So, discuss, having discussed the previous questions, okay, let me now go on to the class. So this is assignment number 11. So let me put forth a question. Like, if you would have gone through the class notes, then you would know that there is a Klingberg-Landau parameter which tells you like the relation between the penetration depth and the coherence length. So penetration depth is something like how far the magnetic field penetrates into your superconductor. That's what will be your penetration depth. And coherence length is something like when electrons are moving, there will be a phase associated with these ones, right? And how long, till what length scale they can maintain that phase, that is what is known as coherence length, or what you also call size of Cooper pair, because Cooper pair is a concept in which the two electrons are there and they are coupled such that, and with their phase basically. And so that's essentially a size of a Cooper pair. Sometimes it's also known as order parameter variation scale. So the question is, determine the relation. What is the relation, numerical relation between of Sternberg Landau parameter? Let's denote it by kappa is equals to lambda L, which is your penetration depth, and chi L, which is chi is essentially coherence length. And determine it by the numerical relation of Sternberg parameter for type 1 and type 2 superconductor. So let's say the options are given. Why to take options? Let's just see it how it goes through. So if you follow the class notes, you will see that the Ginberg-Landau parameter kappa equal to lambda L by epsilon L. So first, the important point here is to understand the length scale meaning. That's what is more important, and then of course there is a proper derivation which you can go through. That will give you this numerical relation, that what will be the value of this kappa. But experimentally, what you measure is penetration depth and the coherence length. These two things you measure, and from the ratio, if it is less than 1 by root 2, you call it to be type 1 superconductor. If the ratio is larger than root 2, 1 by root 2, you call it type 2 superconductor. That's what how it goes. So experimentally, what is more important is lambda L and chi L. If you know these two parameters, you can tell whether it will be what kind of superconductor it is. So if you take this lambda L, let me just define it. So it is also known as penetration depth. So what happens when you have this thing? Your superconductor is there, let's say. This is a superconductor. And in this superconductor, if you are applying a magnetic field, right? Let's say, it won't allow the magnetic field to pass. But of course, some bit of it will be there inside the skin of this material. So it will be expelled like this, right? So it will be expelled like this. Some bit of it will pass through the maybe your superconductor, and this some bit is what is known as this region in which it passes. This is penetration depth. How far magnetic field penetrates into superconductor? Because after a certain penetration depth, it won't allow the magnetic field to pass. So penetration depth is how far magnetic field penetrates into superconductor. Into the superconductor. So this is about the penetration depth. So how do you determine it? Of course, you can have like if your magnetic field is there, you can see the variation in the magnetic field. And these magnetic field variation can be seen with, let's say, if you are having a current, so there are different ways you can sense the magnetic field. Of course, with the magnetometer, you can sense this magnetic field, but let's say till this point your magnetic field is there, and if you put a loop in which this magnetic field threads and there is a change, then you, from the Faraday's law also, you can determine. There are many ways you can uh, determine whether how far your magnetic field has traveled in the skin of your superconductor. So you determine this parameter lambda L. Then there is a parameter xi L, which is what we call the coherence length. This is coherence length. Coherence length generally mean that if, let's say, an electron is there, right? Like this is a system in which an electron is there. This red part is an electron. It has its associated phase with it. It's traveling like this, maybe some randomly it's traveling like this. And if it is deflecting, it means there is scattering, right? Till what length scale, average length scale, till which it maintains its phase, right? A wave function, let's say the wave function of the electron is phi, it is the function of, let's say, k momentum, and then it has a phase e to the power I phi or I alpha. Let's say. This is the phase part. If an electron is traveling, how far it can maintain this phase before losing the information of the phase vector. So this is what is known as coherence length. And in case of your Cooper pair, your one electron is here, another is here, let's say, or somewhere inside the system. So to maintain the communication of phases between them, the coherence length has to be of that order. If the coherence length is larger, it then the Cooper pair can be far distant from each other. If the coherence length is very small, then the Cooper pair has to be, the two electrons has to be very nearby. That's how you can think of. So if I just write it, so coherence length is nothing but size of your Cooper pair size of Cooper pairs. And this is also known as the order parameter variation scale. Now, if we come to, okay, this coherence length you can also measure through these phases basically. Uh, and there are many experiments through which you can see these coherence length kind of thing. Basically, you do the temperature dependence also. So to see how your phase decays, how your this temperature, critical temperature is changing with the uh, increasing temperature, increasing magnetic field. All those experiments you can do to determine the coherence length. And once you know the coherence length and this penetration depth, then you can take the ratio, which is what we call this Jingberg-Landau parameter, kappa lambda by chi. And if your kappa is less than 1 by root 2, then it will be a type 1 superconductor. And if it's a type 1 superconductor, it will exhibit a complete Meissner effect. And if it's a complete Meissner effect, it means it won't allow the magnetic field to pass through it. It will be perfect diamagnetism. And after a critical magnetic field, it will lose. And after critical magnetic field, at C, it loses the superconductivity. Right? So this is about the type 1 superconductor. For type 2 superconductor, the kappa is larger than 1 by root 2. And they allow this partial penetration of the magnetic field. Right? So they will be mixed state. In mixed state means the vortices, right? And then which will allow the partial magnetic field to pass, and then there will be perfect superconducting regions which will not allow the magnetic field to pass. So it's a mixed puddles kind of thing. So they exhibit mixed state, what we call the vortices between, there will be two critical field Hc1 and Hc2, which allowing the magnetic field to pass. After Hc2, there will be no superconductivity in the system. So so essentially what it means is, if your penetration length lambda is less than your chi by root 2, basically your length till which your magnetic field is passing or penetrating is less than your coherence length by some factor, constant factor, by root 2, then in that case it will be a type 1 superconductor. But if your lambda is the penetration till which it's happening in the system of the magnetic field is larger than is your coherence length by root 2, then it will be a type 2 superconductor. Then it will allow the magnetic field to pass and will characterize into the type of 2 superconductor. Along with this, so this is about the conventional superconductivity, but you can see there are unconventional superconductivity which you can read about. Unconventional superconductivity, which people are still figuring out what's the mechanism behind it. They don't know. They're scratching their head, and it's the current ongoing research topic, at least in the case of the condensed matter. So if you take one sheet of, let's say, the graphene, right, and you take another sheet of graphene, which you can of course exfoliate, for which the Nobel Prize was given in 2005, and you rotate it such that the angle, this twist angle, this angle between these two, this angle is magic, what we call the magic angle. At least the condensed matter community calls this theta as, if it is around 1.1 degree, this is what we call magic angle. What happens, graphene itself is like semi-metal, but when you twist them such that there comes a region where it becomes superconductor. Something which was metallic, now it's superconductor because of the interactions. And this is what is currently going on, which goes beyond what we know about the superconductors. So uh, this is about superconductivity in graphene. So having said that, if there is any question you can ask, else we'll move on to the next question. Okay, if no such question is there, then we'll move to the next. I'll put for the next question, which will be about the Meissner effect, and which you know very well because we discussed it in the last class. So let me put for the question. The question is, consider. I'll give four options, and on basis of that, you will have to tell me which is the correct one. So regarding Meissner effect. Choose the correct one. Statements. So either one can be true or more than one can also be true. So the first option which I put forth is, which we call A, is that the outcome of application of magnetic field application of magnetic field is history independent for both superconductors and perfect conductors. B, the outcome of application of magnetic field is history dependent for both superconductor and perfect conductor. Third, the outcome. So history dependence mean if you like, let's say, in which direction you go. Like let's say if you are going from 0 to 1 Tesla or 1 Tesla to 0, before applying magnetic field, you applied any magnetic field, right? Whatever in which order you applied the magnetic field. Do the order matter or not? That's what it means. The history dependence means. So the outcome of application of magnetic field is history independent for superconductors and not for perfect conductor. And the outcome of application of magnetic field is history independent for for perfect conductors but not for superconductors. Yeah. So which of them is true and which of them is false. Since you know the Meissner effect, you know about the perfect conductors, like let's say copper, let's take the copper and gold to be the perfect conductors. Then, which of these is true and which of these is false? Yeah, I don't see any response in the chat box. Am I audible or not? I don't see, because I doubt whether I'm audible or not, because I don't see any response. Okay, C is true. I see. Yeah, and why do C is true? Is there any reason? Yeah, somebody's timing. Okay, let them type. Okay, I don't know how long it will take. Okay, so let me start the answer then. Solution. So before understanding it, though I don't know how many of you were there in the last class, so let me just go over the Meissner effect once, and then about the perfect conductor, ideal superconductor, and then we will discuss based on it. The answer will automatically show up that which one of the given options is correct. So starting from the Meissner effect, so it is a key feature of superconductors. First thing you should always keep an eye on. It is a key feature of superconductors, and it is one of the features which differentiates the superconductor from a perfect conductor. So, what is a perfect conductor? A conductor which has maybe the zero resistivity, right, and infinite conductivity. That's what we call a perfect conductor. But a superconductor is something which also has zero resistance, but along with it, it expels the magnetic field. And the expulsion of the magnetic field, which is perfect diamagnetism, an example of perfect diamagnetism, is what uh, basically uh, calls as the Meissner effect. So when a superconductor is cooled below its critical temperature, right, it turns superconducting. Superconducting means resistivity Rxx is zero, right? And it expels the magnetic field completely if it is a type 1 superconductor, completely from their interior. So essentially, this is not just a zero resistance, but an active diamagnetism response, right? So this is zero resistance plus active diamagnetism response. And the point to note is this expulsion of this magnetic field will happen regardless of whether the magnetic field was applied before or after the transition. So what it means is like, let's say uh, you have two approaches. Initially, your magnetic field, let's say, is zero point 0.1 zero point 0.1 millitesla, and you start cooling your superconductor. Start cooling, let's say aluminium, which is your superconductor. Then after critical temperature, it will not allow this magnetic field to pass through it. Initially, it will allow when it is at say above critical temperature. After critical temperature, initially it will allow the magnetic field to pass. But after critical temperature Tc, right, or I should write below critical temperature Tc, what will happen? It will not allow this magnetic field to pass, and it will go like this, what we call the perfect diamagnetism. Here it is a superconductor. Or you can have a different state in which your superconductor is already below aluminium, below Tc, which it means superconductor. And now on top of it you apply a magnetic field. So what will happen? It will just expels. So it doesn't care about the history, whether before it was applied or after it was applied. It doesn't care about that. So this means this response is history independent for superconductor. So outcome of application of magnetic field is history independent. For superconductors. Now let's talk about these perfect conductors. So perfect conductors are the one which they have the zero resistance. Okay, so someone wrote in the chat box, as in the case of one, magnetic field is applied, temperature greater than critical temperature, and if it's cool below T, then it will be expelled. But this is not a critical thing. It's passed by electrical cooling, it will not expel the magnetic field. This is correct. But if magnetic field is applied, it passed, then if it is cooling, it will not expel. This is correct. So in if but, okay, the first part is correct. Let me think on the second part. As in the case of supernova, when it is applied, then everything will be temperature. Full blue tissue, then it will expel the magnetic completely. It's not a perfect conductor. It is passed, then irrespective of cooling, it will not expel the magnetic field. But that does not tell about your history dependence, right? It just tells you that perfect conductor will not expel the magnetic field, and a superconductor will expel the magnetic field, but it does not tell about like how, in what order the magnetic field applied and how does it affect. So the first part of your response is correct. The second one needs some correction, which I will discuss in this one, and that will clear your doubt. So the perfect conductor are the one which have the zero resistance. So they have zero resistance, but does not expel or does not exhibit the Meissner effect. Exhibit the Meissner effect. This is about their nature. But now, if let's say if a magnetic field is present before the system becomes a perfect conductor, right? Let's say, I mean, uh, a perfect conductor is not something which is always a perfect conductor. Let's say if you cool it down below a critical temperature, right? It turns a perfect conductor. So, in a case of perfect conductor, if earlier the magnetic field was applied and you cool it down then further, it turns perfect conductor. From normal conductor, it will turn into perfect conductor with zero resistance. But the point to note is that the magnetic field will be trapped inside that state. If it is a magnetic field is trapped, next time you apply the magnetic field, so it will be like B1, let's say B1 was trapped, and B2 now you're applying outside, so it will be B1 vector plus B2 vector, which will be there inside. So it depends on the earlier one, what was applied, the magnitude of B1, initial one, right? That's why they become history dependent for perfect conductor. So what I mean is like if a magnetic field is present before the system becomes a perfect conductor, it can get trapped in. So the final magnetic field inside depends on the history, system's history. So this one is history dependent. So if I have to write it, I will write that the outcome of application of magnetic field is history dependent for perfect conductors. And if you match combine this part which I let me call 1 and part 2, you will see that option C will be the correct one. The outcome of application of magnetic field is history independent for superconductor and not for the perfect conductor. Yeah. And now let me just take a very easy example of the numerical part, just to keep this numerical part also going, which is based on the current density and the current, critical current basically, uh, that a wire can carry, right? So the question goes like, a superconducting wire with a critical current density JC, let's say that is around JC of 1.5 into 10 raised to power 7 ampere per meter square has a cross-sectional area A of 2 into 10 power minus 6 per meter square basically. Then calculate the critical current. IC in amperes. So this tells you a very important thing that a wire can carry, and which I will discuss. So what you see from here is the parameter which is constant for a material is at a certain temperature, of course, and certain magnetic field is the critical current density. This parameter, you can think it like is roughly constant for a material. So from here you can determine what will be the critical current in your system. So if you are designing something, so based on your critical current, uh, whatever magnetic field you want to take out of it, let's say you want to make a superconducting magnet, so you need a solenoid kind of structure. You will wrap it around a solenoidal structure. You will pass a current, and below the critical current, it will be superconductor. You will see superconducting state and large enough magnetic field, which you certainly can't achieve with normal conductors. So that thing. Now comes this part, which is the area. Let's say you want to make two wires, superconducting wire, one of this area and another of area 2A. Let's say you want to make an area A wire and another of area 1 by 2A, half the same. Then the critical current will also change depending what is the width of that wire. So the relation between the current density and the critical current goes as JC. Current density is always current, critical current by area, cross-sectional area, A. And in this case, A given is 2 into 10 power minus 6 meter square. Since you are given JC, you are given IC, the A, you are need to determine IC. So IC will be JC times A. So if your area is A, your IC will be 1.5 into 10 power 7 into 2 into 10 power minus 6, and this will be amperes. So 330 amperes. So up to 30 ampere, your wire will be superconductor. If you pass a current which is more than 30 ampere, let's say 30.2 or 30.5, 31, 35, anything above this, your wire will turn to be a normal metal. And this is very important when handling the MRI systems, when handling any superconducting magnet, that this process happens very instantaneously. So if your solenoid is there, let's say your solenoid is there, right, in which uh, let's say around 100 amperes of current I was passing. Uh, for this one is 30 ampere, but if I increase the cross-sectional area, I can make it to be 100 ampere, right? So let's say 100 ampere I am passing, and then there will be self-inductance L of this wire also. If it is a superconductor, its self-inductance will be half Li square, right? Which is huge, large, because 100 amperes you are passing. If somehow your critical current exceeds 100 ampere, and which is also I is equals to IC equal to 100 ampere. Okay, your state will be superconducting, your system is good. Okay, fine. But if your I becomes larger than IC, then there will be avalanche in your superconducting region. Some bit of it will turn into resistive part. Let's say this part turns into resistive. If it turns into resistive, there will be IR square heating, which is very large because I is 100 amperes. This will make this full system turn into normal metal. And if this happens, this half Li square will be turned, it will be dumped into the system instantaneously. Let's say initially it was around temperature of 4 Kelvin. Once this happens, the temperature can go up to 100 Kelvin within a fraction of second. And when this much sudden temperature change happens in your MRI system or any superconducting magnets, whatever, wherever you will go near MRI room, just ask them what happens if you pass very large current. What will happen if you turn off the cooling? Let's say if they turn off the cooling and their system goes above 6 Kelvin, then also their magnet will quench. This is what is known as quenching of magnet or quenching of superconducting magnets. And this happens in fraction of second. Let's say if they stop the cooling, somehow the light goes, liquid helium they were using, that boiled off, they don't have the cooling source, then also it happens in fraction of second. And that full MRI room or the superconducting magnetic the people work on will turn into will fill with helium. If they're working with helium, the full room will be filled with helium, and then people have to evacuate immediately. That's why these critical current numbers are very important, because they have to run the magnets below this critical current. They can't go above this one. If they go above this one, superconductivity will be destroyed. Instantaneously energy will be dumped into the system will get warmed up, things can get damaged. So that's why these critical currents are so important in the scenario. And if you will make the wire more thicker, you can have the larger critical current, as you can see, because this is given as I is Jc times A. But if you increase the area, essentially your wire will become more and more thicker. So you need more and more windings to generate the magnetic field. So there is always an interplay. Yeah. So having discussed this, let me just then take one more numerical question, which is question. Before that, let me just take a BCS theory uh, question, which will help you maybe. So this was around question number, I think, third. So this was question number 3. So this will be question number 4. So in the species theory of superconductivity, what roles do phonon play in the formation of Cooper pair? And this I want you guys to answer, because if you would have attended the class and then you know the answer of this question. Anyone who would like to answer this question? They can write in the chat box. It's open. I think 5 or 6 guys of you are there in the class, and I would really appreciate if any one of you can answer this one. So there are, I think, we total are 10. So at least one or two should be able to answer this question. This is an easy question. The BCS, the fundamentals of the BCS. Okay, let me give you then options also. Option A, phonons are responsible for repelling electrons, creating Cooper pairs. D is phonon facilitates the attractive interaction between electrons, leading to formation of Cooper pair. Third option is phonons have no impact on superconductivity. No impact on superconductivity according to BCS theory. And the phonon increases the resistance of superconductors. I think somebody has answered it. On the two when people will positive spin and have different sign of
Sir,
activity.
option 2.
Okay, so someone is saying option 2, phonon facilitates the attractive interaction between electron leading to formation of Cooper pair. Correct. This is the correct option, and the reason is also, if you would have attended the class lectures, then you know. But I will discuss it slightly further. So, what is phonon? Let me ask, what is phonon? Anybody who would like to answer this? Is what is phonon?
Sir, it is the quanta of elastic waves.
The correct one. So, if your atoms are there and they are vibrating, so they're quantized vibrations of atoms, you can say, right? So, this is what we call, and in a crystal, we know, right? These atoms are like this constant distance apart, right? And they're quantized vibration of atoms in a crystal is what we call the phonons. So, having seen the phonon, now we can, since we know that this is has to phonon is something which is associated with just the vibration of the atoms, then we can go on seeing how it plays its role in the BCS theory. So let's just see it. Since we know the two electrons, they, because of the Coulombic repulsion, Coulomb force, like charges repel each other, right? So they can't come close to each other. according to the Coulomb force theory, right? Uh, but in BCS theory, something interesting happens, right? So in normal situations, electron repel each other because of Coulomb force. Electron repel each other due to Coulomb force. Again, this is single electron theory, this Coulomb force. When you have a flat band and there are too many electrons which are there present, and your potential energy dominates over your kinetic energy, then thing goes into the multi-particle physics, and there you see the interaction physics. But in BCS theory, something interesting happens. Interesting happens. And what is that something interesting? So when an electron moves through a lattice, right, it distorts the positive ion lattice towards it. So, and a lattice has positive ions and the electrons are free in it. Like we treat them as free, they are moving around those lattices. And since when electron passes through those lattices or atoms, it it distorts these positive ion lattices. So, an electron moving through the lattice distorts the positive, distorts the positive ion lattice, right? And now this distorted, basically, this distortion, which is essentially an atomic vibration, right? This creates this lattice vibration and what we call a phonon. So let's say, let me just draw it. So this is your, this is your lattice, and when electron is moving, electron has passed, electron is moving like this, and electron has passed. So what it will do? It will attract these ones, right? And they will come nearby. So their position will be slightly shifted towards the downside compared to the other one. And this vibration will continue, right? It will come down, then electron will pass here, then like in this direction, these will distort, and this will create these phonons, right? So this distortion creates a phonon, what we call a lattice vibration. Now this phonon, because of this phonon, it attracts another electron. In that particular region, your positive charge density will increase, and that will attract the another electron. So that phonon attracts another electron, and that's what we call the Cooper pair. So nearby, and if it attracts it, the next step will be, because of this attractive potential or attractive interaction, right? It forms an effective Cooper pair. So let me write, this creates effective attractive potential forming a Cooper pair. So even though these electrons repel each other directly, right? The lattice vibrations, basically these phonons, mediates an indirect attraction between them. right? And this is what leads to the formation of the Cooper pair, and what we in at least in the BCS theory, that's how we see it. Right? So if we see the options, the phonon facilitates the attractive interaction between electrons, leading to formation of Cooper pair. That's why the option B, as many of you pointed out, is correct. We can say that when electron interacts with the lattice, then a phonon emission takes place. Yeah, you can say it like that also. It's just a vibration of the atoms, right? So in the quantized form. So you see it in the, mm, so you take it in the terms of spring. So you can treat them as a spring, right? So this is something we do in the basic condensed matter. So what we do is we treat like they are coupled with a spring. Of if it's a one kind of system, we treat this of the equal spring constant k, right? And then we do the modeling, like we displace this one by delta x, right? And then based on it, we determine its frequency. What will be the frequency of these oscillations? And that frequency will basically, that's the frequency of emission of your uh, quanta of your vibrations, and that's what we call the phonons. And then the phonon spectra, you solve this Einstein model, and where you have these acoustic phonons and you have these optical phonons, which are on the higher energy. Acoustic ones are, I think, on the lower energy. So the spectra goes like this, if I remember, and for the optical, then it comes like this. This is energy versus wave vector of the frequency omega, I can write. That's how it goes, I think. So this is about it, and let me just see if I can take any more questions, which at least which I can finish on time on this class. Otherwise, we will be having a next class definitely, and that one we can discuss this BCS theory in detail, and maybe one more or two or four more numericals, and the doubts which you will be having can be discussed in that class. So I think the question which I have right now are will take more than 30 minutes and will exceed the time of the class. So having said that in the mind, we'll conclude this class. If you have any question or doubt till this point, we can discuss it. Else we'll be having the class on Monday. We can have it on Monday or Tuesday. These two days are available. You guys let me know when you want the class to be, on Monday or on Tuesday, and around what time would you like to have that class. So there you can prepare for your different doubts or questions which you have, and you can ask me in that class. I'll be answering those questions, and if I am not able to answer those questions directly in class, I will definitely write it to you or email or in the chat box of this class, where you will get the answer to your questions. And please let me know the time and the date. And so could you please send some more NPTEL material on Ising model regarding this course? Definitely, I will upload regarding this Ising model. In this class only, I discussed around 4 or 5 problems. Total, out of which around 2 words of the Ising model. But I will be sharing some notes which I'll upload, and those notes will include more of the problems based on the Ising model, and I can additionally provide some notes on the Ising model also, which are definitely will be there on the internet, but from some good books. Yeah, that's something which I can do. So I will upload from my end. I will upload problems along with solutions, right, on the Ising models, and the notes you can find out on the internet. Definitely, some good books are there. So that we can do. And Mansi is saying on the Tuesday. Let me just see. Tuesday is what? Tuesday is 14. Sorry, so we'll have to. I'm really sorry. We'll have to finish it before 14. So 13 is the deadline for the course. So we'll can only have it on Monday. And Monday, what time? Is evening
Sir,
fine for
7.
Monday? Okay,
Sir,
7 in
7
the,
p.m. onwards, sir.
okay, 7 p.m. onwards. Okay, 7 p.m. onwards. Is Is the time works for everyone?
Yes, sir.
Okay, okay, then we'll keep it on at 7 p.m. I'll request the NPTEL team to drop you a message that the class will be at 7 p.m. in the evening. And when are your exams? Have you guys got any date for your final term exams for this course?
24th of April.
24th of April. Okay, you have plenty of time to prepare. I think 14 days are there, so you can prepare that one. That's an easy one. Anyway, I will be uploading all these class notes and additional notes also uh, with the additional problem solved, so you can just refer it for more of the numerical questions. And as far as I know, the mm, and the question paper will also be inspired from the assignment questions only. So if you prepare the assignment notes and the assignment lectures properly, and will just follow the class notes, you will be able to just do it well in the exams also. That's what I think. And having said that, I will conclude the class for today, right? And if you have any
One
questions,
question I wish to ask.
yeah, please ask.
Sir, regarding the examination, what typology of questions would we expect that it should be only numerical based, or some theory questions will also be there?
See,
Like,
as in the assignment, you can see. Uh, for example, this is from the assignment only, from the class assignment only. And that's why I'm referring myself to class assignment so that you guys get an idea of what how the exam will be. So there will be a question, and then there is this true false kind of thing, right? Choose the correct option, right?
yes, sir.
This can, yeah, this can be there. Then additionally numericals will be there, definitely numericals will be there, you know. And that's it. Basically it doesn't matter how the exam comes up, because sometimes it's on the supervisor how do they uh, basically form their exam, but it will be mostly inspired from the assignments only.
Okay, sir. Thank you.
Yeah, okay, bye bye guys, have a nice day.